I want to welcome you to another statistical topic. And I want to say, up to date, all recordings are published. You can check, you know, a YouTube channel. Of course, you're actually going to have access to all recordings. Even this is being recorded now. I'm also going to publish that later. So I want to welcome you to another statistical topic. And of course, today's topic is very, very crucial to not only to statistical world, but to the world of research in general. So today's title is Power of Test and Nema-Pearson Lemma. Okay, in the outline, I'm going to talk about simple versus composite tests. Let me quickly say this. At times when I upload lecture material, I normally update. Okay, so please, because I want to believe in life, things are changing. So make sure you always check for the updates. Now, in my lecture today, I'm going to, since we want to figure out the power of a test, we need to be able to know the type of test that we're talking about. So I'm going to make a clear distinction between simple tests and the composite tests. Then from there, I'm going to walk you through what I call likelihood ratio tests. Then from there, we go to power of a test. You're actually going to see the connection between the power of a test and type 2 error. And lastly, so what make a test to be most powerful test? Of course, today, I'm going to walk you through that. Nema and Pearson gave us a way to be able to derive the most powerful test. Now let's get started. I'm actually want to start with simple and composite tests. Now let me tell you this. Um, you know, when we normally want to conduct a test, if we want to test how valid is the values of a parameter we hypothesize. I told you the other time, our mind can never be empty. We always have something occupying our mind, like we normally have an intelligent guess about what the value of a parameter is going to be. You know, when I know the probability distribution of my population, where I want to choose a sample of data from, every probability distribution is parameterized. Some have one or some have more than one parameters. Okay, one parameter may be known and the other one may be unknown. The one that is unknown is what we actually going to hypothesize about. Because the one that is unknown, okay, maybe through intelligent guess or whatever, since our mind cannot be emptied, we have a certain value in mind, and the only way to see whether what we have in mind is actually right or not is to conduct statistical tests. Now, let me tell you this. We got two different type of tests: simple tests and composite tests. So what do I mean by simple test? How am I going to identify a simple test? How am I going to identify a composite test? I need you to listen. If I want to talk about, if I want to identify whether it's simple test or composite test, I need to be able to, I need to look at the nature of the alternative. In a situation where I need you to take a look at this example now, the probability distribution that we actually want to sample from is an exponential, and the alternative hypothesis is given like that. Theta equal to 3. Maybe in this case, maybe the non-hypothesis is 2, or maybe something greater than, but the alternative, the moment the alternative is given as like this, of course, this is a simple test. Because talking about the distribution, if I plug in 3, okay, then what that means is this is uniquely specify the PDF under that alternative hypothesis. But let me tell you this, in the situation, the alternative is greater than or less than or not equal to, that would be a composite. Composite in a way, because that, when I say something greater than something, it means there's so many values, not just one. And that is never going to guarantee a unique expression of that probability distribution. To answer this question now, this is simple test. Okay, any question? Now let's go to another example. Suppose we are still sampling from exponential distribution, and the alternative is this. Is this a simple test or a composite test? Of course, this is a composite. Composite in the sense that there are so many numbers greater than 2. I can decide to say this is the probability distribution. Somebody can say, okay, it's 22. Somebody can say it's 500. Somebody can say whatever. In this kind of situation, we don't have a unique expression for the probability distribution. Does that make sense now? So if I really want to know whether I'm working with a simple test or working with a composite test, I need to first look, I need to pay attention to the way the alternative hypothesis is being stated. Now, this is how to identify between simple and composite test. But let me tell you this. Take a look at this. What of in a situation where, the exponential that we did the other time only has one parameter? Okay? But what of in a situation where we have a probability distribution that has more than one parameter, like normal distribution? Normal distribution has 2 parameters. It has a parameter of mean and variance. Let's say, for instance, if variance is unknown, right? And we want to test hypothesis about mean, even though the alternative is mu equal to 12. Okay, the fact that the variance is unknown, this is a composite. Then which one is going to be a simple? Okay, the one that will be simple is, okay, one of the parameters is already known, and we are now testing hypotheses about the other one. That's going to be simple. But right now, this is composite. Composite, it's more or less like all the parameters are unknown, and you only have idea about one of them, and that is the one you are hypothesizing. So to answer a question where one of the parameters is unknown, and you are having an hypothetical statement about another parameter, that's a composite test. Then the simple test for this is going to be when the variance is known. You already know variance, but you are hypothesizing the mean. That will be simple test. But right now, this is composite. Now, let me now tell you this. Whether simple test or composite test, okay, as suggested by the nature of the alternative hypothesis, and when whether one of the parameter is unknown or known, we can actually conduct what I call a likelihood ratio test. If I want to test an hypothesis, whether the hypothesis is simple or is composite. Okay? The idea of a likelihood ratio test, when I say likelihood ratio test, the likelihood ratio test is actually want to give us an opportunity to derive a threshold of making a decision regarding hypothesis. Now, for you to be able to use a likelihood ratio test, of course, you need to first understand the probability distribution of the population, from which you want to take your sample of data. Now, and let's say you want to test this hypothesis, the non-hypothesis equal to theta null, the alternative theta equal to theta 1. And of course, by likelihood ratio test, you're actually going to get the likelihood of the distribution. This is not the first time we're going to be working with likelihood. You understand what I mean, right? The Fisher-Nehmer factorization is about likelihood function. Not only that, we work on the maximum likelihood method of estimation. And not only that, if you take a look at the Skefi-Lemma theorem of factorization, it's also about likelihood function. Now, if you take a look at this is a ratio of the likelihood function, of the distribution, assuming the non-hypothesis is true and the alternative is true. And you know what? When we do this, we believe that this guy here is actually going to be less than a particular value, okay, which I'm actually going to call a critical score, a critical region. And if X falls in that region, then we're actually going to reject the non-hypothesis. And that was why you say this: if lambda is less than C, lambda here is a ratio. If it is less than C, it means it falls in the rejection region. What is the opposite of less than C? That would be greater or equal to C. Greater or equal to C actually means acceptance region, and which means we actually going to fail to reject the non-hypothesis. Now, if I really want to work on this, then I need to be able to know. I need to be able to determine the values of the C. And if I want to determine the values of C, then I need to put into consideration type 1 error. Now, this is a likelihood ratio test. Okay, this particular test is being used for either simple test or composite test. Any question? Okay, now we now want to move to the power of a test. Let me tell you this. Whenever we are conducting a test, okay, we need to be able to understand what is the power of the test. What do I mean by the power of a test? Power of a test is the ability to take correct decision. I'm going to say that again. Power of a test is the ability to take correct decision. What do I mean by taking correct decision? When the non-hypothesis, okay, is false, it should be rejected. When the non-hypothesis is true, we should fail to reject that. So the power of a test is the ability to take correct decision. And of course, if I want to conduct an hypothesis, the whole thing is going to start with deriving the test statistic, and that will be followed by rejection region, because we needed to create a threshold, okay, for us to be or be able to take a decision. And the power of a test now is talking about what is the probability that the test statistic actually fall in the rejection region, okay, when the parameter under investigation, okay, is for the alternative. It's because when you reject the null hypothesis, what are you trying to tell the world? You're trying to say the alternative is right, the alternative is true. Okay, that's what we call the power of a test. Now, this is the typical, the graphical representation of a power of a test. Now, let me now tell you this. Whenever we want to figure out the power of a test, our mind should go to type 2 error. I'm going to say that again. What do we mean by type 2 error? The type 2 error is when you fail to reject the non-hypothesis when the alternative is true. That is what we call type 2 error. What is going to be the complement of that? The complement of that is when you reject HO, the non-hypothesis, when the alternative is right, which means type 2 error and the power of a test are mutually exclusive. If I know type 2 error, then I will be able to figure out the power of a test. Okay, the probability of type 2 error and the power of a test, when I add them together, it should be equal to 1. Therefore, if I want to get the most powerful test, then I need a test that will give us the minimum value for type 2 error. Is that not interesting? Because the lower the type 2 error, the more the power. That's what it means. And that was why here, this is a mathematical definition now. I want to test this hypothesis. And the power of a test, now you can see what I put in the parentheses. For the power, I'm referring to the value under the alternative. I'm referring to the value under the alternative hypothesis. Don't forget, I said here the power of a test is rejecting HO when the theta equal to theta A. The theta A is the value under the alternative hypothesis. Okay, now, and if this is the power of a test, then I can also define type 2 error. The notation for type 2 error is beta. If I want to define type 2 error, then I'm also it's going to be a function of the values of the parameter under the alternative as well. I needed to see the connection between type 2 error and the power of a test. Okay, now the type 2 error here is the probability that you fail to reject HO when the alternative is right. Now, I just wanted to see that 1 minus type 2 error now is going to be power of a test. This is a relationship. The power of a test is equal 1 minus type 2 error. I need you to pay attention to what we have in the parentheses here. It is the values of the parameter under the alternative. Is there anyone want to ask question here? Is there anyone? The person that joined online, if you want to ask question, you need to chat, or you need to raise up your hand, and I'm going to allow you to talk in case you want to ask question. The person online. Is there any question now? So the power of a test is equal to 1 minus type 2 error. Let me see, a chat came in. Okay, the person said, okay. Now, I want to move right now. Now, I think I just I've explained this to you the other time. Okay, this is explaining between the simple test and a composite that I've just if lambda equal to 2, if the alternative is like that, the distribution will be uniquely expressed. And it's going to be called a simple test. But in a situation where you have this guy greater than or less than or not equal, of course, you actually, that's going to be called composite. I think I've explained that. I want to move. Okay. This is if you want to see the definition of the simple hypothesis and the composite hypothesis. Okay, the simple hypothesis, I told you that the hypothesis uniquely, specify the distribution when the nature of the alternative is parameter equal to something. But if the parameter is greater than something or less than something, that will not uniquely determine, okay, then we're going to call that a composite. But whether simple or composite, the idea of a likelihood ratio test can be used if you want to figure out the threshold under which the non-hypothesis should be rejected. Okay. This is another example. I told you the other time, you want to test hypothesis about mean, and the variance is known. Okay, that's a simple hypothesis. And on the other hand, if the variance, you want to test hypothesis about mean, but the variance is unknown, that will be a composite. Okay, so whether simple or composite, we can actually determine the most powerful test. And the only way to figure out the most powerful test is if you can use the idea of a likelihood ratio test and set up the threshold, and given any level of significance, if we can determine the type 2 error, of course, the moment you understand, we compute the type 2 error, the power of a test can be figured out. Okay, and you know what? So, we got two people that gave us the idea of constructing the most powerful test, and their names are Nemer and Persson. The Nemer and Persson actually gave us an idea of constructing the most powerful test. Let me tell you this, it's more or less like, where can I get the most powerful judgments? If I want to talk about court of law, in the court of law, what we're doing now, they also do that in the court of law, where they got two hypotheses before the court. The non-hypothesis is that the accused person is innocent. The alternative is that the accused person is guilty. Of course, the law will presume an accused person to be innocent unless it's proven by the law that is guilty. Now, because the court has a territorial jurisdiction, the jurisdiction of the court actually falls in the region where the offense was committed. Then that means you already know the probability distribution. You're going to take your sample size. You already know the probability distribution of the population. But how can we get the most powerful judgments in the courts where we already know that very court has a territorial jurisdiction in law to entertain the case in the first place? The same thing in statistics, where you know the distribution you want to sample from, the probability distribution has to be given. You have to know that distribution because that is where you want to take your sample size, your sample of data. How can we get the most powerful judgments? Then to get the most powerful judgment, then that very court need the most powerful threshold. What is the threshold now? There's going to be a threshold, and it is that very threshold you're going to base your decision on. And how can we derive the threshold? That the Neyman-Pearson theorem, Neyman-Pearson actually used the idea of a likelihood ratio test, and they believe that if I'm able to set up the threshold using the ratio of the likelihood, and if I get the best critical region, which is the best rejection region, because that is what I'm going to use to decide the case given the value of level of significance, the maximum probability of committing type 1 error, then among every other critical region available with the same size, level of significance is 0.05, then the one with the minimal type 2 error. Because I can have alpha to be 0.05, and I have different kinds of type 2 error, but the minimal, the one with the minimal type 2 error is actually going to be the most powerful, because the power of a test is 1 minus type 2 error. The more, the lower the type 2 error, then the more the power. That's what we mean. And that is going to be called the most powerful test. So in the most powerful test, you need the most powerful critical region, which is the rejection region. So if you use the best rejection region, of course, you're actually going to have the best test that we call the most powerful test. I need you to take a look at this example now. We got a test, and they wanted to find the most powerful test with the significance level alpha, which is the probability of type 1 error, equal to 0.05. You actually want to test, theta naught, that the null hypothesis theta equal to 2, and that the alternative theta equal to 1. Of course, this is a simple test, right? And we already know the probability distribution, and they want us to figure out what the most powerful test is going to be. Now, if I want to figure out the most powerful test here, then I'm actually going to use the idea of Neyman-Pearson lemma. The Neyman-Pearson lemma, which is this guy here, that is a rule. That's what we need to do to be able to, obtain the most powerful test. The most powerful test is also called the best test. Now, what are we going to do? We're actually going to start with the likelihood function of the distribution. Okay, when you take a look at this distribution now, okay, now we want to get it because why do we need to get the likelihood? Every distribution is specified based on one observation. That is for just one observation. But you're not going to take care of one sample size. Then we need the likelihood of that, which is going to be the joint PDF. Now, take a look at this guy now. What are we doing here? Okay, what are we doing here? What we're actually doing here, let's first see based on one observation. Let's look at the ratio of the two. When you take a look at this guy now, plug in theta to be equal to 2. That would be 2y. Plug in theta to be equal to 1. Okay, I think that's going to be 1. Okay, what do you have? When you look at the ratio now, okay, I first want to apply this to just one observation first. That will give me 2y. When I have 2y, according to Neyman-Pearson lemma, that will be less than k. Then I'm going to have 2y less than k. Now, when I go to y less than k, then I need to be able to figure out k. 2y less than k. Now, if I want to figure out k now, by solving for k, then I'm actually going to have my rejection region to be equal to that. Any question? And now my rejection region is y less than k over 2. I just solve that mathematically. This is the reason why in high school, algebra 2, or you actually normally work with inequality equation. Now, when you have y less or equal to k over 2, k is a constant, right? If you take a look at this guy, k is a constant. I can even call k over 2 to be k star. That's another constant. Constant divided by 2 will give another constant, and I'm actually going to call that k star. And right now, I'm going to call my rejection region y less than k star. Now, you know what I need to do now? When I specify my alpha to be 0.05, okay, I want to figure out what k star is going to be. Now, don't forget, what is alpha? Alpha, the probability of type 1 error is equal to the probability that y falls in rejection region when theta equal to 2. When theta equal to 2, okay, y fall in the rejection region where theta equal to 2. Theta equal to 2 is a known. It's for the known hypothesis. Don't forget that is type 1 error, right? So we want to, and that probability of type 1 error now, if we assume that to be alpha equals 0.05. Now, if I want to figure that guy out, then I need to find this probability. Y less, where do I see my less? Look at the regression region. Then less than k, then I need to be, because I'm working with a probability density function, and what is the lower bound here is 0. I'm going to go from 0 to k star because I said the probability of y less than k star. And in my probability distribution, I'm actually going to plug in where I see theta. I'm actually going to plug in 2. When I do that, the whole of that will be equal to 0.05, which is equal to the probability of type 1 error that you choose. Choose a 0.05 here. And in the end, we're actually going to go, at the end of the day, when you solve for k star, okay, your k star is actually going to be 0.2236. So what you are trying to tell the world now is we're actually going to reject the known hypothesis is if y is less than 0.22361. Now, we are now set, we can now find the power. If you want to find the power now, you can decide to first find the type 2 error. And whatever you get in the type 2 error, 1 minus that is going to be power. And you know what? We can also solve for power directly. Now, take a look at this now. I want to obtain power of a test. Why do I have 1 in the parenthesis for power? Because in my alternative hypothesis, okay, the value in the alternative hypothesis is actually theta equal to 1. I told you the other time, when you want to figure out power, then we're actually going to focus on the value under the alternative hypothesis. The value here is theta equal to 1, and that was why you actually see power into 1, means theta equal to 1. And what is power now? Power is the probability of taking correct decision, which is going to be, what is the probability that y falls in the rejection region when theta equal to 1? When theta equal to 1 means when the alternative is true. When the alternative is true, the probability of rejecting the non-hypothesis, that's a good decision. That's what we want to find here. And let me tell you this, which means this is what we actually want to find. That is a mathematical representation of that, the probability of y. You see why we need to first find k star. Without you finding k star constant, there is no way you'll be able to determine either type 2 error or the power. Now, I want to find the probability of y less than 0.2236 when theta equal to 1. Now, when theta equal to 1, now don't forget that 1 is the value of the alternative. What I'm going to do, I'm going to go back to the distribution. Okay, I'm going to go back to the distribution given, which is this guy. And what am I plugging? I'm plugging 1 where I say theta. And, I think that is going to be 1. Okay, that is why what I'm going to integrate, I'm just integrating 1 from 0 to 0.2236, which means if your K star is wrong, then your power is going to be wrong. Now, at the end of the day, okay, what do I actually have? Now, what we got now, the power is 0.2236. Now, I said, even though the rejection region gives the maximum value of power among all tests with alpha equal to 0.05, okay, now, if I know the power to be that, I can determine the type 2 error. Type 2 error will be 1 minus power. And power will be 1 minus type 2 error. Now, take a look at now. What do you see? Oh my God, the type 2 error is very, very huge. Even though your type 1 error is 0.05, but your type 2 error is very, very large. Take a look at that. Now, I'm going to go into another example. Okay. And this time around, we want to sample from normal distribution. And pay attention to this. The variance is known. Okay. And if the variance is actually known, it's a simple test. Okay. Now, the null hypothesis is mu equal to mu naught, and the alternative mu greater than mu naught. Okay. For a specified constant mu naught, then they need you to find the uniformly most powerful test. Okay. With a significance alpha level. Now, we're going to go the same way we went the other time. Okay, we are testing 2 hypotheses. We need the likelihood of a normal distribution. Okay, this is the normal distribution. Okay, and this is the likelihood of a normal distribution. Before I actually come here, you will realize that here the type 2 error is very large, right? What happened? The decision here was based on just one observation. And you remember the other time I said, if you want to minimize both type 1 and type 2 error, what do we need to do? We need to take more sample size. But in this example now, for normal, we don't want to choose one sample size. We really want to choose, more than one sample size. Then we obtain the likelihood. Okay, this guy here, okay, is actually, give me 1 second. So this guy now, okay, is the likelihood of this distribution. That's what I mean. Okay, so getting the likelihood now, then I actually need 2 likelihood. Okay, all what I'm just gonna do is to start subtract, plugging in. Okay, now when you take a look at the likelihood of normal distribution now, when you take a look at the first one here, okay, I'll plug wherever I see mu, I put mu naught. Mu naught is the one under the null hypothesis. And take a look at the one in the denominator. What do you say? I put mu A. Any question about I'm using the Neyman-Pearson criteria, where when I get the likelihood function of the distribution, all I just need to do is to plug in what you have as value in the null hypothesis, to also plug in what you have in the alternative. Then you're going to find the ratio of that. Then we're going to write less than K. Now, all what we just need here is to simplify. We're going to have an algebraic simplification. Now I need to simplify right now, simplify now. When you simplify, there's something I need to pay attention to now. Take a look at this guy and this guy. Because the variance is already known, they're going to cancel out. You're just going to be left with the exponential, okay? Then you simplify that exponential, just gonna have one exponential, then you're gonna have, from here now, from here now, you're actually gonna move here. Any question? Is there anyone who have a trouble time understanding how we're able to arrive at that? Any question here? Is there anyone want to ask a question? Okay, now if I have that guy now, what is the next thing we're gonna do? Mathematically speaking, if I want to remove the exponential, I'm gonna take the log of both sides, and I'm actually gonna have, you know, I'm gonna, and the log that I'm taking is gonna be the natural log. You can see what happened? Taking the natural log of both sides, that k is not gonna have a natural log, and the natural log of the exponential will eliminate exponential. You're only gonna have, so what you see here now is the exponent of the exponential here. Do you see that now? We're using mathematics now, mathematical knowledge now. I used to tell my students in statistics, particularly those that are doing theory of statistics, the knowledge of mathematics, of algebra and calculus is actually required. Okay, now, when you simplify, at the end of the day, take a look at this. Y bar greater or equal to that? Initially it was less than, right? But don't forget, situation where you have a negative at the other side of the inequality is going to change the inequality sign. And at the end of the day, for mu A greater than mu naught, like the value in the alternative, if it is greater than the value in the norm, okay, right now, this is what you're going to get. Now, when you take a look at what you have in the right-hand side, you're actually going to be seeing sigma squared, right? That's already known. The total is known. Then mu naught and mu A, those are known. The only thing that is unknown is K. But let me tell you this. The whole of the expression at the right-hand side, the whole of the expression here is C a constant. Okay, I'm going to call that K star. Why am I calling them K star? Because in the expression here, I already have a K. There's going to be another constant, right? And if I want to rewrite that, I'm actually going to call this my rejection region. Y bar greater than K star. So if Y bar is greater than K star, okay, then I'm going to reject the null hypothesis. Okay, don't forget. Now, which means if I want to know whether this is the most powerful critical region or the most powerful rejection region, then I need to be able to obtain the power of a test. Now, if I want to obtain the power of a test right now, okay, I need to first start by assuming a value for the probability of type 1 error. Okay, so what do I want to find? I want to find K star. I need to be able to find that K star. Don't forget, if I want to take a decision, right, I need to know what the values of K star is. Don't forget, the K star is my threshold. So if I see if the values of Y bar now here is greater than the threshold, then I'm going to reject. So that threshold you created is crucial. Okay, so what I need to do to get it, I don't just decide on K star. I need to put into consideration, the level of significance. Okay, somebody, I think, okay. So can you go over the algebra in the left side at the bottom of the slide? Okay, let me see. Are you talking about? Is the person talking about this page? Are you talking about this page? Okay, let me see. The person said, no, one before. Okay, so one before, are you talking about this one? Is it this one? The person online, give me 1 second. Is it this page? Yes, bottom of the page. Okay, now, when you talk about the bottom of the page, that is the knowledge of math. You know what I'm trying to say? This. Cancel this, right? Mathematically speaking. But when you take a look at this now, give me 1 second. When you take a look at this guy now. Okay, in mathematics, when you have exponential raised to power a divided by exponential raised to power b, if I want to go by algebra 2 or 1, if I want to rewrite this is going to be exponential raised to power a minus b. Do you now understand? We're using law of mathematics here. That was why you can see here we only have one exponential, and what they carries now is just, this minus that. Okay? So I believe, and if you need more clarification, somebody, the best say, yes, I see now. Now, if you need more clarification, I need you to meet with me during my office hour. Okay? Now, the next thing I'm going to do now, I need to get a K star, which is the probability of Y bar greater. Where is the greater coming from? Don't forget. That was what I don't change the sign, greater. Okay. Now, and don't forget, what is Y bar? The Y bar as a random variable here is from a normal distribution. Then the idea of a z-score will be used. Okay, what do I want to figure out? Okay, star. And this is the same thing as this guy. Okay, that is the same thing as that guy. If you know what we did before on the inverse normal, I want to get K star, then that is going to be, if I remove that, the inverse, then it's going to be Z alpha. Then I'm going to check from the table. And by the time you solve, your K star is going to be that. You remember that we did it before. Your K will be hypothesized value under the non-hypothesis plus the number of standard deviation. Don't forget, what is standard deviation of the Y bar is sigma over root n, and the Z, where Z is going to be the number of standard deviation away from that. Now, with that, you're going to get your K star. Okay, now, and that will be easy. The moment you get your K star, everything is going to be nice. Now, I quickly want to walk you through this example. Now here, we make a derivation. In the end, this is what we got. The same normal. Now, I want you to pay attention to this. If mu is less than mu1, what you have in the non-hypothesis, if it is less than what you have in the alternative, we're going to use S bar greater. But if mu naught is greater than what you have in the alternative, if mu naught is greater than what you have in the alternative, that's a lower tail, right? Okay, then it's going to change. The critical region is going to, all what you just need to do is to reverse. I just need to take note of that. Now, right now, let's assume if this guy is this, then you want to find the C star, it's going to be that. Okay, and you're still going to make use of that. That was the, instead of C star, I'm saying K, instead of, so that is the same. Now, you can, and you remember the other time, I walk you through the sample size determination when you know the value of Z alpha and Z beta. Okay, now let me quickly go into the last example here. I'm going to spend, okay, I got 2 more minutes. Take a look at this. Let's assume that you are given all this. You're given the sample size, the 2 hypothesized value, the standard deviation, and they say determine the critical threshold. And not only that, determine the type 2 error and determine the power of a test. You need to first find that C star, that C, that constant, right? That constant gives you 0.329, and the test, the rejection region now is this. And take a look at this. Situation where mu naught is less than mu1, 0, 1. Now, we can now find type 2 error. If you want to find type 2 error now, take a look at this. Find the type 2 error. If the rejection region is greater than, if you want to find type 2 error, you're going to go opposite. less than. Okay. And if you go less than, what are you using? You're using this guy here. You see that? You plug in what is Z alpha, what is mu naught, what is all of that. And by the time you do that, okay, that will give you, oh my God, look at the type 2 error. The type 2 error is very, very small. Even what was the sample size here? The sample size was 25. The type 2 error is small. If you get the type 2 error to do that, what is going to be the power? Oh, look at the power. 1 minus type 2 error, that is 0.99996. Okay? The last slide. This is just to remind you of what we've done before. If you want to get the minimal sample size when you are given the mu naught, the mu1, the sigma, and the alpha, by the time you plug it that in, 8.6, that will be 9 observation needed. This is going to be the end of my lecture today. But before I go today, okay, before I go today, I need you to attend the revision next week. We're not going to have new lecture next week. I'm only going to walk you through Monday and Wednesday next week. I'm going to walk you through practice problem, tell you expectation in the midterm too. So I need all of you to be around. Okay? I'm going to tell you what the expectation is going to be. I'm going to, whatever you need for the exam too. And after that, the other week is a Thanksgiving week, right? We're only going to have in-person lecture on Monday of the Thanksgiving week. Why on Wednesday, the lecture will be on Zoom? Because I know some of you will travel for the Thanksgiving. There's not going to be lecture on Friday of the Thanksgiving week. Does that make sense? Make sure you all stay safe and have a lovely weekend. Bye for now, everyone.